In these notes, we're going to learn how to apply the characteristics of quadratics to real-world application problems. Campers at an aerospace camp launch rockets on the last day. So an aerospace camp, aero meaning air, and space, decide to launch rockets. So think of fireworks on the last day. The graph below shows the path of one group's rockets. So down on our graph, this is the way the rocket moves. So I'm going to first look at my x-axis. I know that it's using time to measure the x-axis, and we're using height to measure the y-axis in feet. That's always good for me to orient myself to the graph first. So this is the graph for launched rockets. So we're comparing height and time. So number one says, how high did the rocket go? Well, I know that my vertex or maximum tells me the highest point on the graph or the lowest point. In this case, it's going to be the highest point on our graph because it's concave down. So the highest point on the graph corresponds with, we'll say 575, because in between 500 and 600, we're a little bit above the halfway point, so I'm just going to say 575. That's an estimate. It doesn't have to be accurate. So now that's the highest that the rocket has been launched. The second question asks, at what time does it reach this height? Well, if I want to figure out the time of this, I'm going to follow my vertex point downwards towards my x-axis, which represents time. I notice that the vertex or the maximum lines up with 6 seconds, which means at 6 seconds, the rocket reaches its highest point in the sky. The mathematical terminology for this point, like we've already mentioned, is the vertex, or in this case, the maximum. They are the same thing. That's why it's so important that we've been focusing on figuring out how to find the vertex. My fourth question asks me, what is a reasonable domain for the graph of this rocket? Remember, domain refers to x values. You learned this in 8th and 9th grade. So I want to look from the leftmost side of the graph to the rightmost side of the graph. Well, I know that we start at 0, and this is going to be seconds because we're talking about the domain, which is the x values. So 0 seconds, which means x can be equal to 0 or greater than 0. But I also know that the graph stops at 12. So that means x is less than or equal to 12. The domain represents time. Again, domain means x values. Our x values are time. So in question number 5, we're going to say the domain represents time. And if we want to relate this to our word problem, it represents the time it takes for the rocket to be launched to then come back down and hit the ground. So from 0 seconds when it's initially launched, it takes 6 seconds to get to its highest point, and then another 6 seconds to get back to the ground, which puts us at 12. So the domain represents the time it takes for the rocket to return to the ground. The initial value. What is the initial value of the rocket's launch? Well, we know that initial value is synonymous with y-intercept. So we're going to go to our graph and look at where does our graph touch the y-intercept? Well, our graph starts at 0, 0, right at the origin. This means that at 0 seconds, the rocket has a height of 0, which makes sense. We haven't started yet, So the rocket hasn't started launching. It's going to be at 0 feet when it is at 0 seconds. Number 7 asks, what does this mean in the context of the problem? It means that the rocket hasn't been launched yet. At 0 seconds, our rocket hasn't been launched, which is why it is at 0 feet. So if we go back up to our graph, we could see that at 2 seconds, the rocket is at 300 feet. At 4 seconds, the rocket is at 500 feet. At 6 seconds, we already know that it's reached its maximum of, what did we say, 575-ish feet. At 8 seconds, it's now back to 500 feet. And at 10 seconds, it's back to 300 feet. And at 12 seconds, it's back down to the ground because it's lining up with 0. So at 12 seconds, the rocket is at 0 feet. If it's at 0 feet, that means it's back on the ground.